All right, welcome everybody. We are recording and I am sharing what we are up to this go around is the models, the mathematical equations and models for competition. So we're going to essentially take the logistic growth model, which you learned about in our last video, and we're going to add interspecific competition, which we talked about in a previous lecture, the ideas of how two species compete with each other, and how the niche that they share or they don't share affects dramatically whether or not they slow each other's population growth. Okay, so there's a little outline of what we're going to do in today's lecture. We're going to review logistic growth because it is the building block for all of the future models. We're then going to add competition to that logistic growth, and two old famous guys that worked this out were Lotka and Volterra. So they have been long called the Lotka-Volterra models for competition. We're going to remind ourselves how equilibrium matters. Equilibrium, you'll recall, is any place that growth equals zero is a place where there's the possibility for coexistence between two species. Growth being zero might not sound like a good thing, but for example, we learned that the carrying capacity is the size of the population where growth is equal to zero when you've met the carrying capacity. And that is actually an optimistic thing for the stability of the population, because we learned it was a stable equilibrium. If you go above your carrying capacity, you get knocked back down to it. If for some reason you're below your carrying capacity, you grow back to it. So we'll look at equilibrium in a more complicated scenario where there are two species interacting. And so we need to think about two species competing with each other, and we need to think about what their dual equilibriums might be. We will review the assumptions of this model like we always do at the end and point out how it's most often very simplistic and there's complexity that would need to be built into a more comprehensive, realistic model. And we'll finish talking about competition by looking at some old lab work done on paramecium, which essentially supports the ideas that we're going to identify in our Lotka-Volterra two species competition models. Okay, so hopefully you recall this slide. This is the logistic growth equation. The growth change in n, that's population size, over some interval of time is equal to exponential growth, which is r times n, multiplied by 1 minus n over k. Okay, so you'll notice this is all about one species. In fact, there's only one species involved. They don't even denote which n we're talking about because we're only talking about one species here. This was intraspecific population that we were modeling, intraspecific population growth, intraspecific competition, determining the population growth that we were modeling with logistic growth. So it has the R for one species, it has the K for that species, and it defines the growth of that species. And we learned that it's exponential early on, and then as you start getting halfway to the carrying capacity, you start to decelerate, and while you still grow, and it's still going up, you slow that growth as you approach K. Okay, so you can return to that Zoom lecture if you want to review logistic growth, because it is the foundation, the building block of all of the future models. Okay, so fundamental thing about logistic growth is the carrying capacity, and it is a function of intraspecific competition. How many members of the same species do we need to have before growth slows down and goes to zero? We talked about how that could be competition for resources. just exploiting the resources, or it could be actually physically fighting through interference. Doesn't matter. It's going to have the same effect on population growth and competition. And essentially what it models, logistic growth models, as the density goes up, as N goes up, the growth rate that is realized goes down. That's modeled by having this factor K and by essentially making population growth density dependent. As N goes up, R goes down, and we do that by factoring in K, or the carrying capacity. So here's a little cartoon. Say this is a population, this rectangle, and however 10 or 12 or 15 squares we have are individuals. And we, in this population, that's the number of individuals that you can have, the N population size, before you reach K. Okay, because there's no more room. Of course, it looks like you could fit another one in right there, but let's just trust for the cartoon's sake. This is the carrying capacity for a species based on its logistic growth and its carrying capacity. But here's where we want to switch gears from intra-specific competition to inter-specific competition. The notion, and the very simplistic notion, that you don't just compete with members of your own species or population. Oftentimes, if you have overlapping niches, you compete with other species. You probably compete with multiple other species, but we're going to stick to the simple case of two species competing with each other, two different species competing with each other. So if we refer back to this situation where we used to have a carrying capacity of 10 or 12, now if there's this second larger, heavily dominant or aggressive or big or competitive big yellow species, what happens to the carrying capacity of the first species? It goes down. So this makes sense. If you share resources, not only are you going to get to your own carrying capacity and be limited, but if there's another species that relies on those same resources, either exploits them before you can get to them or beats you up so that you can't have them, your population growth is going to be limited even more so. And therefore, your K might be the same, but we now need to factor in the number of members of the other species, species 2 we're now going to call this, that and model quantitatively how that slows your own species population growth. So in this case, we used to say, well, species 1 population growth is largely determined by the fact that it is close to its carrying capacity. But now when we consider species 1 and species 2, we see that there are many fewer individuals of species 1 that can exist. The population growth is going to slow, not when we get to 10 or 12, but it's slowing already when we're at 8 or 9 because of interspecific competition. And the Lacke-Volterra models that we're about to go over are going to show us both quantitatively with formulas and then graphically with what we're going to call zero growth isochrones, how this happens. Okay, so Lacke-Volterra competition includes two species. So you're going to have to worry about the numbers of two different species, N1 and N2. You're going to have to worry about the R value of two species, R1 and R2. These are two different variables. This is not R1, R2, one variable. This is just telling you that you need to be worried about the N, the R, and the K of two different competing species. We're first going to worry about the population growth of species 1, and that comes about in this formula. Recall that I told you guys last time that you will be allowed to have one-sided 8.5 by 11 piece of paper where you by hand write notes. I don't want you printing out in like -4 font every living piece of information in the world. But you can have one sheet where you write down the graphs, the formulas, the definitions that you feel are most critical to have on hand for exam 2. Okay, so keep that in mind as you are thinking about memorizing and preparing for the exam. What we have here is the formula for the population growth of species 1. That's how we know, because it says DN1. What is the change in the numbers of species 1 over a given time t, it is equal to the exponential growth of species 1, R1, N1, multiplied by this ratio, okay? The bottom of the ratio is the carrying capacity of species 1. The top of in the numerator, we find the difference between N1 and K1. So everything so far is all about species 1, but the final term minus alpha 1, 2 multiplied by N2 is the one factor that introduces interspecific competition. It is factoring in some number of the other species you're competing with, N2, multiplied by this competition coefficient. Alpha 1, 2 is the effect that species 2 has on species 1. Okay, so you just need to memorize that. If I'm interested in the growth of species 1, then the alpha I need to consider is the effect 2 has on 1, alpha 1, 2, multiplied by the number of species 2 that we are competing with. Okay, so exponential growth, logistic growth, carrying capacity accounted for. This is the term that Volterra got famous for, the competition coefficient minus the number of the competing species. Notice that this is a subtraction. This is always negative. This is always going to drain off population growth because the assumption is that you are being negatively affected to some extent by the other species. When we look at mutualism, the reality that two species can sometimes help each other's population growth, this will become a plus, and population will go up based on the number of the other species because that species is helping you in a mutualism. Okay, we can do this all over again for species 2, and you can check your notes here and just verify yourself. Now we're talking about the growth of species 2, so we include the exponential growth variables of species 2. We consider the carrying capacity of species 2 relative to the population size of species 2, and we then subtract off a product, which is the number of species 1 that they're competing with, and the alpha competition coefficient, which describes how negatively species 1 affects species 2. So N matters, but also the alpha competition coefficient matters. Worst case scenario for species 1 is that there's a lot of species 2 and they're very damaging to the population of growth of species 1. That would make this a big negative number that would really drain population species 1's population growth. Okay. So just to review, the competition coefficient for species 1's growth is alpha 1, 2, the effect 2 has on species 1. What I just said. Alpha 2, 1 is the competition coefficient that we want to include when we're interested in the population growth of species 2. It is the negative effect that species 1 has on species 2. So if you're trying to remember which one goes in which, the first number tells you which species growth you are concerned with. The second number tells you the competitor that you're worried about. So species 1's growth is determined by alpha 1, 2, the negative effect of 2 on 1. Species 2's population growth is determined in part by alpha 2, 1, which is the negative effect 1 has on species 2. We do this just mathematically, and we're not going to get into deep math with this. We're trying to make N1 and N2 equivalent. We're trying to make this not apples and oranges. So the alpha allows you to convert the number of members of the other species, the competing species, multiplied by the alpha, and it turns everything into equivalents of the members of the same species. Okay, there's the equation again for species 1. And this is just restating. We're trying to, in the numerator, make members of the other competing species equivalent by multiplying by this competition coefficient. So if this is a big number and 2 has a very negative effect on 1, we're going to essentially be seeing that as alpha 1, 2 is greater than 1, the impact of species 2 on species 1 is more negative than the impact of species 1 on itself. In other words, we know about logistic growth and we know about the carrying capacity. and we will know what K of species 1 is. But if alpha 1, 2 is a number larger than 1, and if it's much larger than 1, that's a way of saying in the equation that species 2 has a very, very negative effect on species 1's growth. It's even worse than adding members of species 1 itself. Vice versa, if alpha 1, 2 is a less than 1, then the impact of species 2 on species 1's population growth is less than the impact of species 1 on itself. Okay? So bigger than 1 alpha, the other species is just killing you. Smaller than 1 alpha, well, it's not helping because it's competition, but it's not as bad as members of your own species. So this, where it's less than 1, is probably a case where you don't share the niche with species 2 that badly. When alpha 1, 2 is really negative, you share a niche and the other species is really slowing your growth. If it's equal to 1, mathematically, that's just a way of saying it doesn't matter. Adding more of your own species or adding more of the other species is going to have mathematically the same effect on your own population growth. Okay, so those are the equations, and do get familiar with them. I want to remind you that when we looked at logistic growth, we looked at this graph. This graph was mainly about equilibrium. And we noted that the carrying capacity right here is an equilibrium, and extinction right here is an equilibrium. And they are both equilibrium because equilibria are in population sizes where growth is 0. And here, the carrying capacity growth is 0 because that's the definition of a carrying capacity. That is the size of the population when you can't grow anymore. Extinction is the same thing. Theoretically, it's less interesting because it means that the species doesn't exist at all. So population growth being 0 and the carrying capacity might seem like a negative thing to you, but it's actually a hopeful thing. We don't want species growing out of control. We don't want our own species growing out of control because that's when you hit famine. That's when you outstrip your resources. That's when lots of people start dying. Stability in ecology comes from equilibrium. It comes from finding places where your growth is 0. Now remember, growth being 0 doesn't mean you're extinct. It means you are just resting. If it's a stable equilibrium, you're resting at a certain population size. And as we learned with the carrying capacity, if you get bumped off that, it's a stable equilibrium and you move back. And if for some reason you're pulled back here, you can grow back there. There is stability in finding an equilibrium because when growth is 0, that means you're not exploding out of control and you're not shrinking to extinction. You are a stable place. This is going to become even more important when we talk about two species, Laca volterra, interspecific competition, because now, how do we find out what the population sizes are for two competitors where you might actually get to keep both species? If we're conservation ecologists, if we want to know how species could coexist and we could build biodiversity, we need to know what are the combinations of N1 and N2 that lead to maintaining both species, and what population sizes actually, according to the models, will lead to the exclusion of one species by the other species, and thus losing biodiversity. Okay, so we're interested in equilibria when we start talking about zero growth isochrones. Zero growth isochrones are essentially this graph, except it's got to be more complicated because now we got two species and we need to know where does each species find zero growth, and that'll tell us where we can expect them to coexist and where they should not coexist. Okay, so an equilibrium is just where growth is equal to 0 for both for species 1 and then for species 2. Mathematically, it is a place where this numerator that we talked about is equal to 0 for either species 1 or species 2. So that's interesting to consider. Mathematically, if you wanted to derive these equilibria, you could just solve for where that numerator is equal to 0. We're going to do it a little differently and more graphically. Hopefully you're a visual person and you can work better with graphs than you can with equations. At least I'm that way. But I think these equations will make sense more when we look at it graphically. So what have we done here? We have graphed now two species. Always put species 1 on the x-axis. Always put species 2 on the y-axis. Why? Because I said so. And because, hundreds of years of ecologists before me have always said so. Do this to keep things straight. First thing we're going to do is draw a line or an isocline where species 1 finds 0 growth. Okay? Realize that this line is just a series of points. Every point, everywhere you go in this graph space is some number of species 1 down to the x-axis and a paired number of species 2. Here, there's very few species 1 and there's very few species 2. Here, there's a ton of species 1 and there's very little species 2. Here, there's a ton of species 2, but there's very little species 1. And out here, there's tons of both. Make sense? Okay, so I've drawn this 0 growth isocline. And you can't draw a line if you don't have two anchored points, right? So the easiest place I want you to go for species 1 is to species 1's axis. And note that the point that we draw our line from is at its carrying capacity. This makes sense. K1 should be on the N1 axis at a place where species 2 is extinct. So K1 is some number of species 1 where species 1 has 0 growth, but species 2 is extinct, does not exist. So we've just restated what we already knew from logistic growth. If there was no species 2, right, we're at 0, then species 1 is going to have 0 growth at its carrying capacity. Okay, so this point is K1, and what its value is doesn't matter at this point. It's just some number. If we pull it out here, that means the carrying capacity is higher. If we pull it in here, the carrying capacity is smaller. But the other side of the line is some number of species 2 where species 1 doesn't exist. So here's one of those weird mathematical things. We're trying to solve for the population growth of species 1. And to do so, we need to find a point at which species 1 is 0. Species 1 is going to have a hard time growing if it doesn't exist. But doing this mathematically allows us to solve this equation. And if you solve this equation right here, making species 1 extinct, then you will find that N2 equals K1 over alpha 1, 2. The number of species 2, N2, you need to have species 1 have 0 growth when species 1 equals 0 is K1 over alpha 1, 2. Okay, once you've done that, you have drawn a line here, and with the origin of the graph, you have a triangle. And what you can say is that every graph point inside the triangle is a place where species 1 is growing. And everything that is out here in the graph space above the 0 growth isocline is a place where species 1 is shrinking. Population growth is declining. Sometimes it helps me to actually prove this and explain myself why this is. What if we say carrying capacity here is 75? But let's say that species 1 is actually at 100. And let's say there's very little of species 2. If we're right here, I can actually want to do something kind of fun. Laser pointer. Oh yeah, there you go. That's hot. Right here, I might ask you on a quiz, what's happening here and why? And the correct answer would be species 1 is declining. And if you think about it, species 1 declining on this graph, in this context, is an arrow moving to the left. Species 1 declining means you're on the N1 axis, you're going from over here backwards, making species 1 smaller and smaller and smaller. And why is species 1 declining right here? Well, largely because it's past its carrying capacity. If you trace this point over to the species 2 axis, you actually see that you're well below this threshold. Right here, species 1 is declining because of intraspecific competition. It's gone past its carrying capacity. There's too many members of species 1 for species 1 to grow here. It's not because of the numbers of species 2, because we are well below this threshold. In contrast, what if I asked you what's going on at this point right here? Okay, well, let's trace it. We got about 15 members of species 1, well below its carrying capacity of 75, but you've got like 100 members of species 2. This point right here is a place where species 1 is declining, just like it was over here, but here it was declining because of its carrying capacity and intraspecific competition, and here it's mainly declining because, not because it's past its carrying capacity, because it hasn't, but because it's way past this threshold. The number of species 2 beating up on species 1 right here is too high, especially given the alpha the effect 2 has on 1. So we just explained why species 1 is declining here and why species 1 is declining here. You could do the same thing within the triangle and say, why is it growing in here? And the answer is some combination of intraspecific competition, K, and interspecific competition, the number of the other species 2, given the alpha 1, 2, is below this threshold, and you're still increasing in here. Okay? If you're freaking out at this point, just hang on, take deep breaths, try to get through the lecture, write down questions, and we will spend all of a week from tomorrow, my first day back. We'll spend the whole time answering your questions about this new material, if that's what it takes. Okay. That's the zero growth isotype for species 1, but we have 2 species. Okay. This is some serious math that I forgot and included. This is really review. It's explaining where we got the anchors for the zero growth isocline. You can also solve that for 0 if R equals 0, but that's not a case that we're worried about. If R equals 0, population can't grow just because of its intrinsic rate of increase is 0. So we just drew the zero growth isocline for species 1 based on its carrying capacity and its interspecific competition value. Okay, so this is all review. This is just solving for 0 and finding those 2 values. If there is no species 2, then the only thing limiting species 1 is its own logistic equilibrium or carrying capacity. As you go to extinction, you can theoretically derive that the number of species 2 that leads to 0 growth for species 1 when species 1 is extinct is this value K1 over alpha 1, 2. That's all review for how we got this. And this is just redrawing what we've seen already. K1 anchors species 1's growth on the x-axis, and K1 over alpha 1, 2 anchors it on the species 2 axis. We learned that population grows, species 1 moves to the right, growing if it's underneath the triangle, the ZGI, and it declines, moving back to the left when it has exceeded its carrying capacity. Oh, let me take that back. It's not just the carrying capacity. We talked about a point right here where species 1 is declining, but it's not because it's past carrying capacity. It's because the combination of the N1 and, in particular, the combination of species 2 is so overwhelming that it can't grow. That it has to move back here. Okay? That's species 1. We now need to do the same thing for species 2, and then we need to put the 2 lines together. Okay? So we are now modeling the zero growth isocline for species 2's growth, dn2 over n2 dt. In other words, the change in n2 over some period of time. Where is that equal to 0? Okay, well, my advice to you is always start with intraspecific competition. If we're interested in species two's growth, let's start with how it is limited by itself. When N1 is non-existent, when N1 is equal to 0, species two's growth is determined by some number of species 2, the carrying capacity, K2, is the place that species 2 has 0 growth, when species 1 equals 0, when N1 equals 0. And you can derive that if you want mathematically. How many species 1 N1 are there when species 2's growth is equal to 0, when species 2 does not exist? Right? This is a place where species 2 is equal to 0. We need this anchor point, even though it's a theoretical point. N2 equals 0 right here. N1 equals K2 over alpha 2, 1. It is this negative effect of 1 on 2 with this many species 1 that leads to 0 growth for species 2. Okay, so just done the same thing for species 2 that we did for species 1, except now we got to use species 2's carrying capacity, and we got to use the effect 1 has on 2 to determine the growth of species 2 through interspecific competition. Just like we did before, everything below the isocline represents growth for species 2, but remember species 2 is on the y-axis, so growth is going from bottom to top. And everything above the 0 growth isocline is population decline for species 2, being on the y-axis. That means going from top to bottom, declining downwards. Everything, if you're wondering what about on y, the line is the equilibrium, called the 0 growth isocline. The whole line is 0 growth. So if you're right here, you have some chance of staying still, except for the fact that we now are going to introduce the competitors to each other. You got to know which species you're talking about, and you got to know which axis they're on. If you're weird, maybe you like 3 dimensions. I personally find it more confusing, so I'm going to zip on past that 3-dimensional. What we're going to do now is put the 2 0 growth isoclines, one for species 1 and one for species 2, on the same graph. It's possible that the lines could cross. It's possible that they don't cross. We'll see both scenarios. And the placement of these lines and the slope of these lines is going to tell us whether or not the competitors can coexist with each other. Where they coexist, where one should be expected to decline, and where one might be expected to grow. If we want them both to coexist, we need to find a place where they both have a population growth of 0. And that's only going to come if their 0 growth isoclines cross. Right? They cross, and they each have a place on their 0 growth isocline where they both have 0 growth, and that is a very optimistic future. But there might be a place where these two could both have 0 growth together. Okay. All right, let's put the lines together. So the labels are the same. The only thing different now, the anchors are the same. N1 is here. It's anchored by K1 and K1 over alpha 1, 2. Species 2 is on the y-axis. It's anchored by K2, and on the x-axis, K2 over alpha 2, 1. You will need to get these Ks and these alphas correct, because if you put the wrong K or the wrong alpha on the wrong line, then it doesn't make any sense. You do need to label the line. You probably won't have color to work with when you're working on exams, so you'll need to write that this is the isocline for 0 growth for species 1. And this is the isocline for 0 growth for species 2, if that's the way you want to draw it. Okay, once you've labeled this as species 1's line, then I know this needs to be K1 and this needs to be K1 over alpha 1, 2. Okay, so we've drawn it a certain way, and notice that we've drawn it in a way that the species 1 line is above the species 2 line. Another way of saying that is that the triangle of positive growth for species 2 is this triangle. The triangle for species 1's positive growth, remember everything below the 0 growth isocline is bigger. Once you see that, once you've drawn that, once you've noted that, you know right away that species one is going to win this game because there is more graph space where it has positive growth than where species two has positive growth. They're both declining out here. This is a bad place for both of them. Species one is winning in this middle ground, and they're both growing in this lower triangle here. Okay? Okay. How did we draw? Well, most simply, we drew it just by drawing the species one line above this. But to do that, you're essentially saying, I want to make the carrying capacity of species one big, and I want to make alpha 1, 2, the effect species 2 has on species 1, small. So counterintuitive caution here. When alpha 1, 2 is small, when species 2 has a very little negative effect on species 1, this is actually way out here, way up here, because this is a ratio, this is a quotient. When the denominator is small, the quotient is big. So by drawing this line out here, I have made K1 bigger than K2, and I've made alpha 1, 2 smaller than alpha 2, 1. What I've just drawn is a place where intraspecific competition and carrying capacity favors species 1, and interspecific competition, the alpha, favors species 1. If species 1 is being favored by both forms of competition, then it's going to win that competition. And that's what we get by drawing the species 1 line above the species 2 line. Okay, this is a review. We've talked about this. I'll go ahead and get them all out here and we can talk about it. These vectors are the population growth predictions for both species in these three regions that we make in this zero growth isocline graph. Down here, both species are growing. Species 1 is moving to the right and species 2 is moving up. The combination of that is that the population should be shoved in this direction. Out here, we've got tons of both. Species 1 is declining to the left and species 2 is declining down. The important point for this competitive asymmetry, we call it, in other words, where one species beats the other, is this middle ground. What's happening in the middle ground? We see from these vectors, species 1 is growing to the right, species 2 is declining down. In the middle region of 2, species 1 is winning, and we have drawn that. We know that biologically because it isn't as pressured by its carrying capacity, right? Species 2 up here, everywhere in zone 2, is being limited by its carrying capacity. It's also being limited by the negative effect of competition. So this is a competitive asymmetry where species 1 wins. And the only thing we would need to do to show the opposite, where species 2 wins, is instead draw species 2's line above species 1's line. How do we do that? We make the carrying capacity and intraspecific competition of carrying capacity a big number. So species 2 is not as limited by carrying capacity as species 1 is limited by carrying capacity. And again, we've made the effect of 1 on 2, the interspecific competition coefficient, a relatively small number. That underneath this bigger number has turned this quotient into a big number that's way out here. This is saying that the effect of 1 on 2 is a small effect, not very negative, as opposed to the effect of 2 on 1. This is a bigger number, making this quotient a smaller value. Okay, so here, down low, they both grow, up high, they both shrink, and in the critical zone 2 of overlap or of competition, the winner is species 2. It is growing up, and species 1 is declining to the left. The prediction in this zone 2 for species 2, in this case, when it is more competitive, is that you will grow to here. And what does growing to them mean? It means over time, species 2 will drive species 1 to extinction. And you will end up with species 1 being extinct and species 2 being at the carrying capacity. We saw the same thing, back up. for species 1. In this zone of overlap, we learned that species 1 is growing and species 2 is declining, and this is the vector, and where does it go eventually? Here. This is the place where species 1 wins, and it drives species 2 to extinction. Okay, so in these middle zones, it's a relatively tough world. One species beats the other because we've drawn it in a way that both K and alpha favor one species over the other. Okay, so those are both situations of competitive asymmetry. The competitive exclusion that we talked about in the last lecture, Gauss's theory of competitive exclusion, where if you share the same niche, somebody's going to lose. Somebody's going to be driven out by the other if your niches overlap too much. Okay, so to make for competitive exclusion, we had to tweak the carrying capacity and the alpha to lead to one species winning. If you want species 1 to win, make K1 big relative to K2 and make the effect of species 2 on species 1 less negative than the effect of species 1 on species 2. Okay, that's what we're saying here. We have two more scenarios to consider to get through the zero growth isoplans for interspecific competition, and that is where the lines cross in two different ways. So notice that the labels are all still the same. Species 1 is still labeled or anchored by its carrying capacity, and its carrying capacity divided by alpha 1, 2. Species 2's population growth is anchored by its carrying capacity and its competition coefficient. The labels are all the same. They have to be. What's different is the slope of the lines. And the slope of the line is affected by the value that you give to K and alpha. This is a situation in which we have created carrying capacities that are very small for both species. Do you see how K is a relatively small number here relative to the effect of 2 on 1? And K2 is a relatively small number. When you look at these graphs, if you're trying to figure out what's going on, first look for K. Here you see both species have a limiting carrying capacity. And by that, I mean it's closer to 0, right? It's a small number. When your K is a small number, that means you, your own self, you, your own species, limit your population growth more than the negative effects of the other species. How do we seal that deal? Well, we start by making the K's small numbers and the alphas small numbers. When alpha is a small number, it means that it's a small negative effect of the other species. So when alpha 2,1 is way out here, that means alpha 2,1 is small. When alpha 1,2, when alpha 1,2 is small, the effect of 2 on 1 is not very negative. Here, the effect of 1 on 2 is not very negative. What we've drawn here is a situation in which carrying capacities make all the difference relative to competition coefficients. Another way of saying that is in this graph, intra-specific competition is more important to your own population growth than interspecific competition. That's another way of saying K matters, but your niche is not that similar to the other species. The alpha is not that bad. This is going to turn out to be a source of stability. K is no fun, and it'd be great if your K could be infinite, but what's more vital to the stability of population growth, to equilibrium, is that K, whatever it is more important to limiting growth than alpha. If alpha is really nasty, the other species is going to drive you to extinction. If your K limits you before you get anywhere near a place where alpha limits you, then that's a more stable situation. And that's what we've drawn here. Let's see what happens when we look at the vectors here. This is how we drew it, by making K2 less than alpha 1, 2, and K1 less than K2 over alpha 2, 1. That's how you draw this scenario. I'm going to go ahead and zoom forward and do the vectors for what now are 4 regions. We used to have 3, now have 1, 2, 3, 4 regions that we need to talk about. Region 1 and Region 3 are pretty easy to deal with. They're both the situations where numbers are low enough that both species are growing, numbers are high enough where both species are declining. What's interesting is that in zones 2 and 4, the places where there's relatively more species 1 than species 2, and here there's relatively more species 2 than species 1. What happens in these regions? Well, because we have modeled it that the carrying capacities are small, in these two regions, we'll see what happens in zone 2. In this zone, species 1 declines because it's past its carrying capacity. Species 2 grows because it's nowhere near its carrying capacity, and it's nowhere near the number, and it's not yet to the number of species 1, where an alpha 2 1 would slow its growth. So species 2 is growing here, species 1 is declining. The vector brings you back towards the middle. Vice versa here in zone 4, species 1 is growing, right? It's nowhere near its carrying capacity, and it's not yet to a number of species 2 where its growth is going to be negatively affected. However, species 2 is declining here. It has gone past its carrying capacity, and that is what's really limiting its growth. Notice in all 4 zones that the vector points towards the middle. So anywhere you go in here, or here, or here, or here, or here, or here, or here, anywhere you go, short of extinction, eventually you're going to grow back to this X marks the spot. And if you want to, if you have written notes, which I really encourage you to do, you could fill in a dot here. A filled in circle is the way you oftentimes denote a stable equilibrium. Remember how the carrying capacity was a stable equilibrium for one species logistic population growth? In this situation, for 2 species competing with each other, when their carrying capacities are more important to their population growth than their alphas, we have stability throughout the whole graph. Anywhere you go, right here, you're going to grow back to this middle point. Here, you're going to grow back to this middle point. Anywhere on the graph, you should theoretically move back to coexistence, stable coexistence, meaning if you get here and you get bumped off, you should grow back, unless you get bumped so far that you go to extinction. So that's stability. That's as stable as it gets. Call that stable coexistence. What we had to do, so we had to make the alphas small, both alpha 2 1 and alpha 1, alpha 2 1 and alpha 1 2 had to be small, and the carrying capacities had to be the driving factor. Intraspecific competition needs to be more intense than interspecific competition. That's another way of saying that you limit your own growth more than your niche overlap with another species limits your growth. Okay, we have one more scenario. Again, the lines cross. Again, all of the anchors are the same. Species 1's line is anchored by K1 and K1 over alpha 1, 2, and vice versa. Now the lines cross again, so we have another theoretical point where both species have 0 growth. And again, we have these 4 zones. But let's look at what happens to those 4 zones in this situation. A situation which you'll notice is very different from stable coexistence. Stable coexistence had this as K1 and this as K2. Instead, now K1 is way out here, K2 is way up here. Just the Ks alone should tell you, ooh, intraspecific competition does not look like a very limiting force. Ks are large, especially relative to alphas. The alpha here, the effect of 1 on 2, a very small, relatively small number of species 1 is required before the effect of 1 on 2 starts slowing species 2's growth to 0, and vice versa. This is a very relatively small number of species 2, where the effect that 2 has on 1, and to draw it this way, alpha is going to need to be a large number. When alpha is a large number above 1, that's a way of saying that interspecific competition is more important than intraspecific competition. So having these 2 alphas low, and to have them low means that alpha is a big number because it's in the denominator. When alpha is large and K is large, that's a way of saying interspecific competition is more important than intraspecific competition. The Let's look at what happens. That's how you draw it, by making K1 and K2 less important than alpha. Still gives you the same four regions, but look at what happens now. Zone 1 and Zone 3 both lead to the middle. They both grow here and they both shrink here. Now we go to Zone 2 and 4, kind of the asymmetric zones, and no longer do we find them both pointing back to the stable equilibrium. This is what's called an unstable equilibrium. If you're here, you might get here. If you're here, you might get here. But if you're here, where there's originally more species 1 than species 2, species 1 is going to outcompete species 2, and you should move through time to extinction of species 1 at the carrying capacity of species 2, and vice versa here. If you just ignite the competition with more species 2 than species 1, that interspecific competition has passed this threshold. Species 2 is going to win, grow, species 1 is going to decline, and the vector is going to take you to extinction of species 1 at the carrying capacity of species 2. This is called an unstable two-species equilibrium. Unstable in that if you're here or here, you don't move back to the stable equilibrium. Instead, you have a competitive asymmetry and you lose one of the species to competition. Okay? Exactly at that X marks the spot, both species survive, but in the zones 2 and 4, one species wins or the other species wins. Okay? Which equilibrium or which outcome depends on the initial numbers. If you start with a lot of species 1, species 2 is doomed. If you start with a lot of species 2, species 1 is doomed. And that is again because interspecific competition is a big number, strong and constraining. What I just said there. So what do we do there? To make an unstable competitive equilibrium, we made alphas large. Okay, especially we made k's a large number, so k is not limiting. And we made alpha large, and making alpha large means that that quotient is a small number, and you find the ratio of k over alpha to be closer to the origin than k. In words, we've made interspecific competition more intense than intraspecific competition. So to review, there were 4 circumstances in Locke-Volterra competition. We drew, and you should be able to draw and understand the graphs where species 1 outcompetes species 2, where species 2 outcompetes species 1, where they cross and there's stable coexistence throughout the graph space, and the unstable equilibrium, where the winner can depend on the initial number of each species that you start with. You only get coexistence between 2 competitor species when they don't share a lot of niche space. When niche overlap is minimal, when interspecific competition is weak, you can get coexistence. Remember Gauss's competitive exclusion principle, the idea that 2 competing species cannot coexist unless interspecific competition is weak relative to intraspecific competition. What makes interspecific competition weak? Different niches, different resources, different spaces, different time of day. Think about hawks and owls. They eat the same thing, but they feed at different times of day. So they have some niche divergence. They don't completely exclude each other. They limit each other. Any mouse that a hawk eats is a mouse that an owl can't eat, but they aren't overlapping entirely, and so their coexistence is promoted. Okay. We have looked at the Locke-Volterra model for interspecific competition. It's a model like any model. We've looked at it both the equation and the graphical depiction of it through zero growth isoclines. Tons of assumptions in here. Many, many simplifying assumptions to make it possible. First one I'll mention, probably the most obvious, is that we've only considered 2 species. What species only encounters one other species? What species only competes with one other species? very rare for a species to have a niche all by itself and no one else competes with it. So there's almost certainly a multi-species interaction going on, where species one's growth is affected by species two's alpha, species three, species four, species five, species six, and don't even get me started about the fact that we haven't modeled direct negative interactions like predation. That's what we'll do in the next lecture, is we'll create an equation that doesn't just say you're competing with another species, it's saying another species is trying to kill you. Okay, so all models have these assumptions. The model is only as good as its assumptions are true. There's different kinds of assumptions. Some can be violated, and it's not that big of a deal. Others, when they're violated, it just makes the whole thing worthless. Let's look at some of the assumptions. We've made the assumption that the environment is, with respect to all properties, equivalent. The model assumes that the habitat is equivalent in space. Another way of talking about this is to talk about metapopulations. Remember how there are sources and sinks, and sources have good stuff that allows population growth? Well, the model did not ever say, well, if species one and species two are in a source, then growth is like this, and if they're in a sink, it's like this. It made the assumption that all space is the same. It's random or it's uniform, that there is no patchiness. And that is a simplifying assumption. And if you know very specifically, ooh, that's where species two does really well, you might have to model it differently and say, in that kind of habitat, species two's alpha or K is going to be this. In a different kind of habitat, it's going to be smaller. So if you know that from empirical data, you would have to add that to the model. But the model by itself just assumes that space is equivalent. Time the same way. It's not saying what is this going to be like in May versus August, depending on the thermal limits of the species. It's not accounting for the fact that there's more food in early spring than there is in late summer. It is constant through time, and that is a simplifying assumption. One that if you have the data to build complexity on top of, you should, but if you don't, you can't. These aren't realistic assumptions, but if you don't have data to improve it, you got to go with a simplified model. If it's badly violated, then you need to get an experimental system that gives you data that allows you to tweak the model and make it more complex. Another simplifying biological assumption, all the organisms are, with respect to their impacts on their environment and on each other, identical. Have you ever known a population where every individual had the same impact on the environment? Bigger animals probably get more prey. Bigger animals might be a nastier competitor to the other species than small individuals. Males might be more aggressive and excluding resources than females. Juveniles might not have any negative impact on the other species. But if we're just counting the N of species one, then that model is too simple. And juveniles should not be given credit for negatively affecting the other species as much as adults. So individuals are not identical, and a more complex model would account for that and allow you to better predict what the two species are going to do together. So that's totally not true, and a better model would account for that. Okay, so our hypothesis about nature, in this case, two species competition, is only as good as the model that we can build, the data we have to build that model. We need to know these variables. If we don't know R or K or alpha, then we can't even get started. And you can't figure out R and K and alpha without getting off your computer and going in the field and measuring the population growth, the reproductive capacity of species that you want to understand the growth of. Okay, so we're very simply in Lacovitch-Volterra expressing competition as just this decline in growth with increasing numbers of both your own species and the other species. That requires a lot of data to start with, and that requires even more data to make the model more complex. Okay, just a few more slides here. Ending this lecture on competition, interspecies competition, with a little data, old data, as you can tell from these ancient Xeroxed graphs. So you probably dealt with paramecium and biology labs before. They're a great little study system because they reproduce quickly and they're easy to study under the microscope. Two species competition we're studying. So we've got two species in competition here. This little guy, which is Paramecium aurelia, and this big guy, which is Paramecium caudatum. Okay, so it's a little hard to read. This is aurelia, this is caudatum. And the top one shows you the population growth, time on the X, and I think that's a biomass, but just trust me, this is the number of individuals on the y-axis. So in both species, over time, you see population growth. And you see a pretty beautiful sigmoid curve, just like logistic growth, right? You don't see exponential growth forever because there are carrying capacities. And that's what we see right here with this curve. This is Aurelia separate. And by separate, I mean not in competition with caudatum or the other species. Separate, it grows and grows and grows to a leveling off point, telling us the carrying capacity in this simplified environment for Aurelia is about 200. Jump down here to caudatum and look at caudatum's line separately or alone. In other words, this is just intraspecific competition of Aurelia with Aurelia, and this is intraspecific competition of caudatum with caudatum itself. And you can see they have similar carrying capacities, about 200. That's what they do alone. The other line is what Aurelia numbers do when in a mixed population with caudatum. It grows, but very quickly it starts feeling the leveling off point sooner than it does when it's isolated. Instead, it seems to level off at a pretty stable population size at about half the carrying capacity that it saw when it was alone. So in a mixed population, these two species, Aurelia is stable, albeit at a lower number. In contrast, caudatum, which did quite nicely alone, when it's in a mixed population with Aurelia, its numbers start plummeting. And over time, if you carry this out further, you would find that caudatum goes extinct when it is left in competition with Aurelia. Okay, so even though it's bigger, it actually gets outcompeted by Aurelia when they're in competition, whereas Aurelia can level off and keep its numbers stable. It appears that Aurelia has a competitive asymmetry, and Aurelia is driving caudatum to extinction where they overlap. George Gauss did these early experiments showing that caudatum goes extinct when it is put into competition with Aurelia. They are strong competitors. They share a niche. They both use the same resource in this experiment, that is a yeast, base layer of yeast that they exploit. And we see here experimental data showing a competitive asymmetry. Aurelia wins. So this would be exactly what, say, go back to your slides for species 1 beating species 2. Aurelia is species 1. It is winning in a competition with species 2, in this case, Paramecium caudatum. Competitive exclusion. Okay. Neat little experiment that Gauss then did was he actually messed with the environment. He took the same two species where we had learned Aurelia wins. If you just leave them alone, Aurelia wins. But in an experiment, he went in every day and he cleaned up the paramecium poop. By doing this, he replaced the liquid medium and he found a very different result. When he cleaned up the environment every day and essentially replenished the resources, he found that he could reverse the winner. Caudatum wins when he disturbs the environment like that, and Aurelia goes extinct. So what we concluded from this is that left alone, the competitive asymmetry goes to Aurelia, but a different form of competition. There are multiple mechanisms of competition, and Aurelia is able to win that war when the resources are not replenished. But when you replenish the resources, you find that Caudatum can win. How does he think this is happening? He hypothesized that Aurelia, when it wins, actually pollutes the medium. It takes the resource and it makes the environment inhospitable for its competitors. It's kind of like a direct pollution of the environment for the other species. But when experimentally he was cleaning up after them, Caudatum, just based on resource competition alone, without pollution of the medium, without that more direct aggression, if you will, Caudatum wins. So it's a neat experimental result showing you can switch the winner simply by changing the environmental circumstances that they're working under. One final piece of data or experimental result, two different species now, Caudatum and Berseria. Sorry, this is so hard to read. You can see they have, Caudatum has a carrying capacity of about 200 alone. Berseria is a little more limited, around 100. You put them together and you see, it's almost like you just laid these on top of each other. Caudatum does fine, at obviously a smaller number now in competition with Berseria, but the point is you can see stability. Their numbers are staying. Their numbers are nothing like what they would be outside of competition, but in competition, they coexist. P. Caudatum and P. Berseria coexist. Why do they coexist? In a way that Aurelia does not coexist. The key factor is that they are different. Character displacement, we called it before. They have different niches. And the key here is that Berseria is actually a photosynthetic organism. Caudatum is not. They can coexist because they use different resources. This is a stable coexistence. And the suggestion was that Caudatum is non-photosynthetic. It eats the yeast. So it needs to be near the surface for oxygen. Berseria has a completely different niche. It is an endosymbiotic algae. It is a photosynthetic paramecium. It produces oxygen. And for that reason, it feeds on yeast at the bottom of the test tube. It doesn't need to be near the surface. So this niche divergence allows them to coexist more than P. Caudatum and P. Aurelia, who share a niche. Different species with different resources can lead to coexistence. Weak interspecific competition leads to coexistence, and you know how to draw the graph of two zero growth isocymes that does that. Last thing I'm going to do is, for this video, project a couple of examples of exam questions. Some of these might even be on the quiz that we're going to take when we reconvene. Consider a situation where I show you the graph, I give you everything, and I ask you what's going on here. Is this species 1 winning or 2 winning, stable equilibrium, et cetera, et cetera. Okay. This is another example. This is a different graph. Which one is this? This is another graph. Which one is this? This is another graph. This is the fourth graph. Which one is this? Finally, going back to this single species logistic growth, where is population growth the highest on this graph? Can you solve for logistic growth given certain parameters? These are examples of good exam questions. Another way I could do things is probably with a class your size is just ask you to draw things. What I've done in the past for multiple choice is give you the graph with these 4 spots on there and ask you which answer, A, B, C, or D, labels 1, 2, 3, and 4 correctly. If I want you to draw species 2 winning, which one of these combinations, A, B, C, or D, draws species 2 winning? Do the same thing for species 1 winning, same thing for stable coexistence, same thing for unstable equilibrium. Those are the 4 scenarios. And then lastly, think about questions or challenge yourself with questions where I might give you the graph and I might give you a spot, like an X on the graph. Like, what if the X is right here? Who loses at that spot and why? And you would have to go through the answers. Understand the graph. See that this is a stable equilibrium graph. I know that immediately because I see the K's down low and the alpha's up high. And so I know that right here, the answer is nobody loses. None of the above. Coexistence is possible at that spot. Okay, a couple more slides. Who loses at that spot and why? And of course, you can just pick the spot and the answer will become different. Just different versions of our zero growth isochrones. Okay, that is the end of the slideshow for the quantitative portion of the competition lecture. Again, if you have lost your mind and lost any semblance of understanding, do your best. Back up and go through things multiple times if you have to. Most importantly, come to class next week when we reconvene with your confusion, with your questions. And we will inch by inch get you in a better place. Know that you can't run from this stuff. It is a big portion of this part of the class. It is somewhat quantitative and there's lots of graphs, I understand, but it's not going away. It's a lot of points available on this stuff. The next lecture is going to be the same thing where we talk about the ideas of exploitation, talking about species interactions here, negative species interactions. And then we will look at the equations and the zero growth isochrones for predator-prey interactions. Okay, so you don't want to get left behind on two species competition because you need to know that to be prepared for two species being in an exploitative relationship rather than a competitive relationship. Okay, so embrace it, go for it, get to work on it, write down your questions, and I will see you next week where we will get to work again and see how you guys are doing. Okay, I hope you have a great week without me. Take care of yourself.